Good Tuesday to you, everybody in Gov/Com 603. Welcome to, are you ready for this week? 10 plus 1 makes 11. How's everybody doing? Did you have a restful weekend? Huh? All right, well, let's get this week's video underway with, you know, priorities. Much better. Shortwave coffee, cool little shop in the town that I live in. Now I'm your sufficiently caffeinated instructor here for this week's video. Okay, we have two major elements of the video that we got to cover. First, I want to talk about this coming week's module. And then we're going to go back and look at week 10, and we'll go through the discussion questions and take a look at your answers. Okay, so for this week, we are going to continue giving you some practical hands-on experience with some common quantitative tests. This week, we're going to do a t-test that will allow you to put into practice some of the terms and concepts that we've been going over in class. All right. However, I'm going to split this week into two parts. All right. The first part, which I posted and you'll find in the module week 11, I've got a short video that I didn't make it, but a link to a video for you that will explain t-tests. And I know that we did a video on t-tests. I think it was back in like week 7 or 8. All right, but this is another one. Okay. And then likewise, a video or a reading, I think, that will explain excuse me, I got it backwards. A video that will explain the concept of a p-value, and then one that will explain p-values null hypothesis. Okay, and what do they mean? So I'm going to leave the t-test towards the back end of the week because we covered that a couple of weeks ago. Okay, so in empirical research and in the area of quantitative research, and fear not, in the weeks ahead, we will switch our attention and do some qualitative research tests in these fields. One of the very common tests is the t-test. Now, we talked about that, it was week 7 or 8, okay, what a t-test is, but just to refresh your memory, all right, a t-test examines whether there is a statistically significant difference between either two different groups doing the same thing or the same group doing two different things. For example, two different groups, let's say 5-year-old boys and 5-year-old girls, jumping up and down in the space of 60 seconds. So if we took a group of 5-year-old boys and 5-year-old girls and measured how much, had say 100 in each group, and measured, had each one of them jump up and down for 60 seconds and timed it. And then we took the average between the 100 5-year-old boys and the 100 5-year-old girls. And we wanted to know, is there any significant difference, statistically significant difference, in how much 5-year-old boys can jump up and down in 60 seconds compared to 5-year-old girls? Or is it about the same? Right? We would use a t-test. All right. So two different groups doing the same thing. Or t-test is commonly used for one group doing two different things, one group doing two different things, and is there any statistical significance in the outcome? For example, and this is the classic question, and this was in when we covered t-test, a week ago or 2 weeks ago. I think it's 2 weeks ago. Let's say that we take 1,000 people, just random sample, equal number, men and women, all from about the same age bracket. Let's say 40 to 51. All right. And amongst them, we track how often they smoke. And let's say in terms of our sample that we divided equally, 500 who smoke and 500 who don't. All right. And then we track their health throughout their 40s and into their 50s. And then we see which of the two groups, the smokers or the non-smokers, develop cancer of any kind, whether it's lung or any kind. All right. So one group just people doing two different things, smoking and not smoking, is there any statistically significant difference in the outcome between the two different behaviors by the same group? To determine that, we would run a t-test. All right, well, at the heart of the t-test and some other quantitative measures is something called the p-value. And this is what I want you to study for the first part of this week. So from today till about Friday, and then I'm going to upload a data set and a t-test calculator, and then I will post the question. So if you're looking around in the discussion questions, you're going, where they go? Where they go? They're not there yet. I want you to focus on wrapping your head around the concepts. Okay. We would look at the p-value from a t-test. And P stands for probability. And it's the probability that there is a statistically significant difference here, or a probability that what is going on is just within the range of expected variance. Now, remember, several weeks ago, we talked about the confidence interval. And I told you that for most things in the social sciences, and this is where, political science is part, the confidence interval is 95% and up. So in other words, if you flipped a coin, there's just a quarter, okay, and you flipped it 100 times, 5 times over, and you counted up the number of heads and tails in each of those 100 sets of 5, so it'd be 500 total. The average should be a split between heads and tails, not 50-50, but at least 95%. So it could be 50-50 in some of them, but it could be 98% heads, or excuse me, a split of 98% instead of 50-50. So maybe it's like 49 heads and 51 tails, or 49.5 tails. I don't know how you get a 0.5 when you're talking about a coin flip. Okay, that doesn't work. Okay, but there's a 5% chance of it being not a perfect split. This is just built into how things operate. Okay, a p-value tells you, the p-value is the expression of that remaining percent. Okay, so if the p-value is greater than 5%, this tells you that there's something actually going on, something that is statistically significant. And if the p-value is lower than 5%, then this tells you that no, there's really no significant difference in the average outcome between either the two groups doing the same thing, or excuse me, the one group, the two groups doing the same thing, or the one group doing two different things. Okay, that's the p-value. Now, p-values are used to evaluate something called the null hypothesis. And, in empirical research and statistics, this is a common term. I'm not going to explain it in this video. It's fairly straightforward. And I want you to, when you read the material that I posted, I think you should understand what a null hypothesis is. And if you don't, as we get towards the back of the week, shoot me an email. Say, I'm really not getting this. Okay. But for these first few days of the week, I want you to focus on wrapping your head around t-test, p-value, null hypothesis. Now, if the material that I've supplied to you is not sufficient to have it make sense, and that could work. Sometimes you got to hear things from different sources from different angles. Okay. I want you, and this is why I'm splitting this assignment, I want you to get out there on the vast World Wide Web and find these concepts, these 3 essential concepts in quantitative research for empirical research, quantitative testing for empirical research. Find them explained in a way that does make sense. And these 3 things are the t-test, the p-value, and the null hypothesis. Okay. So and we'll shift back into the text and get back into some terminology and concepts as we move through the second half of the semester. But, for a significant part of the back half of the semester, we're going to be focusing on acquainting you with the actual exercise of the experimental method in empirical research, whether it's quantitative or qualitative. All right. So at the very least, you'll have a comfort, I hope, that's the objective here, with these tests, and or when you read about them, you'll understand what the various terms and values mean. You'll have an experiential understanding. And in fact, when we get into next week, we'll talk about how quantitative research, or people use, I should say, people use quantitative research to lie and cheat. Shock. No one here in this class, of course, within the empirical research field that is trying to pass off things as significant that are not really, and how they can monkey around, and the p-value, affecting the p-value. There are many ways to tell a fib using quantitative research. Okay. Playing with the p-value is probably the most common. In fact, it's so common, there's a term within quantitative research called p-hacking, and it refers to doing things that monkey with the p-value to make it look as if there's not a statistically significant difference into what's going on, or there is, depending on what it is that the empirical researcher wants as an outcome, which is not empirical research. It's dishonesty. Okay, so that's what we're up to this week. So watch the video, read the source, have a good conceptual understanding of what a t-test is, what a p-value is, and what a null hypothesis is. And then in a couple of days, I'll give you a data set and a t-test calculator and ask you to start running the numbers. And just like we did last week, you tell me, what does it mean? But speaking of last week, let's take a look at how you did. So you did a simple linear regression last week. Okay, and the calculator that I gave you is a very straightforward and very simple one. There's nothing really wrong with it, but you can, when you get into this part of empirical research, you can get a number of different values besides r and r squared that will tell you about the relationship between variables. All right, these two values, r and r squared, and then the scatter plot that you can generate using the simple calculator, are perhaps the most useful to you as a researcher using this quantitative method. Okay, because they tell you the two critical, they answer the two critical questions concerning a causal relationship. Namely, is there a relationship, a causal relationship between the two variables, and what direction does it run in? And then what percentage of the outcome, the dependent variable, is being caused by the input, the independent variable? Those are the central questions when you're looking at causation. Because, you remember the example that I gave you about my muddy boots, wiping them or not wiping them, and my wife's bad mood. Okay, so if I wanted to put forward a simple linear regression to say, is there a relationship between, I go out hiking a lot, and in the wintertime it rains here, is there a relationship between how often I don't wipe my boots before I track back into the living room after a hike on a muddy trail, and the level of my wife's bad mood by Sunday night? All right, so I could count, I could construct a study in which I counted the number of times, and I would like say within the course of a month, I would deliberately wipe and not wipe my boots equal numbers of times before I tracked into the house. And then I would just sort of slide a survey over to my wife at about 6:30, 7 o'clock each of those Sundays and go, oh, hey, hon, I was just kind of wondering, could you take this mood survey for me? No reasons, because I wouldn't want to bias my outcome, would you? Yeah, wish me luck with that. But anyhow, imagine that I did, and she took this, and then I took the data from the survey, and then I took the number of times that I didn't wipe my boots. I put those into a linear regression calculator, and I would be looking for the R value, okay, which would tell me, is there a directional relationship, meaning no boot wiping to bad wife mood, or wife bad mood, or is it running the other way? Is it bad wife mood leads to no boot wiping because maybe I'm a jerk and whenever my wife's in a bad mood, like, oh, I'll show you. I want to get mud on the carpet. Now you really got something to be upset about, which I wouldn't because I'm not a jerk. Okay, but we're looking for a directional relationship. So those are the numbers that you're after. Okay, let's take a look at the questions and let's see how you did. Question number 1, using Google, what does a linear regression's R and R square value signify? So here I just, you need to be able to understand when you see these values and they pop up. Okay, what does this thing mean? Okay, Robin, let's take you first because you went first. I said, yeah, I use Bing Copilot. I'm sorry, Robin. Instead of Google. That's fine. I just meant a search engine. Okay, maybe I should just say that. Okay. So a linear. Okay, so here's your answer. In a linear regression, R and R squared are key metrics. Okay, etc. Okay, here we go. Linear regression. It's called the correlation coefficient. This indicates the strength and direction of the linear relationship between the two variables. This value always ranges between -1 and +1. Okay. +1 means there's a perfect positive linear relationship, meaning every time, 100%, every time this happens, this happens. Now, that is in itself an expression of correlation. All right. It is not necessarily an indication of causation, but it's telling you, and we can use our common sense and go, you mean to tell me every time I look out the window and I see snow on the ground, there may have been snowflakes falling from the sky? That's a correlation, right? Because every time, it's like snowflakes falling from the sky and then there's snow on the ground. But is it a causal relationship? When you have a really strong R value, that's an indicator to you that there is causation at work here, not just consistent correlation. Okay. That's the R value. But what about R squared? Oh, so, solid 1 means absolutely every time this happens, it goes this way. -1 means every time this happens, it goes this way. So remember the thing about having it, we're predicting a direction. Okay, that's the R value. Good job, Robin. Okay, R squared. What does R squared signify? R squared represents the portion of the variance in the dependent variable that is explained by the independent variable. Okay, that is true. Let's translate that into straightforward English. Okay. Because this is what you're going to want to do for yourselves and maybe for a final exam someday. I don't know. Oh, wink. Okay, so now that we've established the strength of a correlation, meaning X amount of percentage of time that this happens, independent variable, the other thing happens, dependent variable. Maybe there's a relationship. Well, let's ask. R squared tells us, and again, R squared is a value from 0 to 1. Okay, R squared tells us how much of what happened, the dependent variable, is actually being caused by what's happening, the independent variable. And 0 means not at all. And 1, and these are usually expressed as 0.0 and 1.0, and then fractions of 1 usually expressed in percentage. Okay, so when you see an R square value, a raw R square value as well as an R value is written in a decimal. So just times that by 100 or just move that decimal point over 2 places to the right, and that will turn it into a percentage. Okay. So 0 meaning no causal relationship to a perfect 1 meaning 100%. The 100% of this outcome is being caused by this income, this input, this output being caused by this input, this dependent variable by this independent variable. Do you understand? Okay. All right. That's question number 1. Good job, Robin. Question number 2. Then we sort of dive a little bit deeper. I asked you then, what does the R and the R square value you found in your regression suggest about the relationship between comorbidities and severe COVID outcomes? Now, remember, the little article that I gave you. Okay. When you have a virus that gets turned loose in the population, it's going to get around. Okay. So the objective is to reduce the severity of the outcome when the population, members of the population, get the virus. Now, it does happen in some cases that vaccination against the virus, because it allows the body to get a head start on its immunity, can blunt what the virus does once it gets into your body, and therefore blunt the severe outcomes. Okay. Or in some cases, if it's complete inoculation, that is when the virus gets into you in your body, just, manhands, because you had a vaccination, then that reduces the incident. And it's not it's just not perfect. It reduces transmission, that is you giving it to somebody else. Okay, so because for you to give a virus to somebody else, the virus has to be present in your body up to a certain level. And I don't mean literally like it stacks up to your mouth. Okay, and it's called the viral load, without getting into the specifics of what that is and parts per million in your body. Being vaccinated can keep the viral load down and reduce your capacity, your tendency to transmit the virus to other people. So you can slow it down in a population. All right, but ultimately what you're watching for is how does the virus affect the people that it gets? Okay, so you do the linear regression, you take that data table that I gave you of severe outcomes and number of comorbidities from 0 to 2. And remember, as I told you in the video, that they stopped at 2 because they found people who had at least 2, that their severe outcome was so high, it was not statistically significant in the difference if you had 3 or 4. 2 was enough to have an impact on severe outcome. Okay, Andrea, let's take a look at you. There, let's see. So ask you what your R and your R squared mean in the calculation that you did. You said there's a strong relationship between those who possess severe COVID-19. I think what you mean, those who encountered severe outcomes because of COVID-19, have comorbidities and are admitted to the ICU. Okay. Now, Andrea, I'm not picking on you, but for everybody else, when you write out your answers, whether in discussion or in the test, make sure that you get your verbiage all in the right order. Okay. In other words, the severe outcome being ICU, is there any corollary linear relationship between severe comorbidity and any in the ICU? And is there any causal relationship? So that's R. Is there any causal relationship, R squared, between severe comorbidity and ICU as a severe outcome? Okay, so let's see what you did. Let's take a look at your data. In case 1, you selected ages 0 to 17 where the comorbidities were X, that's the independent variable, and ICU, where Y, the dependent variable. That's exactly right. Now, by the way, you could switch those around. All right, the line on the graph will go the other way. All right, as long as you understand what's what and how to read the graph, it doesn't really matter which goes in X and which goes in Y. Okay. So Andrea writes, there's a demonstrably strong and positive correlation between comorbidities and those individuals entering the ICU due to COVID-19 between the ages of 0 and 7. Okay. Now, what you don't have here, Andrea, and what we need is because you report an R value of 0.92. That's 92%. Okay, so how many comorbidities are you talking about here? Is this those with one comorbidity or with 2 or more comorbidities? Okay, so when you're reporting values for linear regression, be sure, like the R and the R square values, be sure to report clearly the data that went into them. Okay, so is this R and this R squared, which is 86, 0.86. That's 86%, not 92. Okay, is that for one comorbidity or 2 comorbidities? Okay, so make sure that you get that right. Let's see. Let's take a look at somebody else. Okay. Let's see. Morgan. Okay. Amber, let's take a look at what you did. Okay. First case, I selected age group 0 to 17. For the first case, For the first case of comorbidities, death rate, my results were as follows. Okay, so what I'm seeing here as a trend, and I didn't notice this when I was putting together this video, but I'm noticing it now, okay, is you have got to report how many comorbidities were involved with the outcome of R and R squared. Otherwise, that doesn't make, it just doesn't make any sense. Okay, well, I mean, it makes sense, but it doesn't tell you about the corollary relationship and the causal relationship. Is the causal relationship is different between those who had one comorbidity or those who had zero comorbidities, those who had one, and those who had two. Let's see if somebody, let's see if there was somebody who did that. It's a ventilator, right? Okay, yeah, but how many comorbidities? Come on. Still no. Okay, note to everyone to class. Make sure that you understand why it is you need to report the number of comorbidities, because that's a variable. Okay, that's a different variable. One comorbidity is a variable. Zero comorbidities is a variable. Two or more comorbidities is a variable. And they're different variables. Okay, here we go. Rebecca, I found that at least one comorbidity. Okay, here we go. There's a strong correlation with R being 0.88, so 0.886, so that's like 89% for children under the age of 18 to have severe COVID outcome that led to death. Okay, I also found the R squared is 0.76, meaning it's also strong causal relationship, 76.8. So 77% of the death in children from 0 to 18 was caused by the one comorbidity. Okay. All right. Make sure that you understand, the variables that you have got to report. Okay. Question number 3. I asked you to screen capture your scatter plot and your R square values. Now, because you only had 3 variables here, all right, three components to your independent variable. No comorbidity, one comorbidity, 2 comorbidities. You're only going to get 3 dots on the line graph. Now, frequently when linear regression is done, there's a whole bunch of those points in the independent variable. And so you will see a whole grouping of dots. This is a scatter plot. Okay. And then the line that the calculator draws for you is about center of where the cluster of dots are. Okay. With only 3 of them, this makes it easy for you to understand and track. Okay. Now, and what this does, what's the use of this scatter plot with the line on it turned into a line graph? This gives you a visual of sort of the slope, the strength of both the corollary relationship and the causal relationship between the two. Okay. So for instance, I'll look at Robin, you posted yours first. We'll just take a look at this graph. Here's percentage of hospitalization with number of comorbidities for ages 60 to 69. That's my age group. Okay. So here over way on the left, 0 comorbidities. The hospitalization was, it looks like about maybe slightly above 10%. So maybe like 12%. Okay. By the time you get to 2 or more comorbidities over to the right, the hospitalization jumps up to something like 68%. Okay. That's a big difference. Okay. So it gives you a visual by which you can say, oh, okay, there is a strong relationship here. There isn't a strong relationship here. There's a high percentage of the dependent variable of what's caused that is being caused by the independent variable, the input. Okay. All right. So finally, question number 4. Recall your experience of the 2021 COVID-19 pandemic. Is it 2022, I guess, too? Do you recall a media emphasis on the causal relationship between severe COVID outcomes and comorbidities? Why, in your opinion, did the media cover or not cover this? Jennifer, when COVID struck, I was in Louisville, Kentucky. The main thing that was covered in the news was the effect of COVID in elderly people. I also heard many correlations between COVID and African-American communities. For us, it was extremely fraught, extremely fraught. You mean fraught? I think what you mean is fraught. To gauge, considering that there were many protests in the streets of Louisville at the time. People seemed not to care very much about social distancing. Okay, a lot of that going around the country. We traveled across country during COVID to my husband's new place of work. When we came to California, most people who were older caught COVID. As far as the death toll is, it's very unclear and confusing because we didn't experience many funerals in Kentucky. However, there were many in the state of California when we moved that we related to COVID. I remember there being a huge media relationship with severe outcome, death rates, causes, ethnic groups. It wasn't until I began venturing out and talking to doctors that I heard about the comorbidities. And I think now some of you say, yeah, I remember hearing something about that, but in general, that is correct. If you look back at the news cycle, and how do I know this? Because I did. There was not only a minimized discussion of comorbidities, there was no discussion of a causal relationship. Okay. Now, I asked you, why do you think that was? And that was kind of sort of a trick question. Okay. Charles, you say the media may not have covered this because the health department did not stress the relationship between these two variables. Many topics were being discussed associated with slowing the spread, developing vaccines, political efforts, etc. And efforts on comorbidities may have allowed lives to be saved by reshaping the efforts of the population to manage personal contact, vaccination, hospital visits. I think may have also decreased political tension and increased voter turnout. Okay. So, yeah, I think, to look back at it fairly, I think you're right, Charles. And there were others like you, others like Charles, that said, there seemed to be an emphasis that the media wanted here. So they reported certain elements and they didn't report certain elements. By way of analysis, I believe that to be true. I believe also part of the reason that you didn't see the emphasis is that people weren't compiling and crunching the data. And now this is one of the things that I want you, as a takeaway from empirical research. As human beings, we tend not to see what we don't look for. And that could be as striking as assuming that the earth is the center of our system, and we just don't really look hard at the evidence that points in a different direction. And even when we do see it, we tend to explain it away. That is, once we get a, this isn't a media conspiracy thing. This is how our head works. Once we get a constructed idea of what the reality is, we tend to lean on that, and we tend to not go looking for evidence to question that, and B, when there is evidence that emerges, we tend not to look into it because of the predisposition. And the reason I put that question in there is this, takes us back, if you remember back in the early weeks of the class, we discussed researcher bias. All right, because researchers are just people. Now, if they're doing their job, they should be investigators, not advocators. They should be following good empirical research design and standards. But people are people, and they don't always follow these things. Okay, everybody, that's it. Half an hour is as long as I'm going to keep you. All right, so for this week, watch the video, read the text, get your head wrapped around t-test, p-values, null hypothesis. And then a couple of few days, I'm going to give you a data set and a t-test calculator, a simplified version, a lot, in many ways, like the linear regression simplified calculator. And you're going to learn how to run a t-test, and more importantly, how to interpret the outcome of a t-test. So when you see it in future, and t-tests are used a lot in political science, you'll have an idea as to what in the world is going on. Okay, everybody? Great week to you. I think about you. I pray about you. I will see you on Canvas, and bye-bye.